Hello everyone, I'm Ilio from Peking University. In this presentation, I'm going to talk about our recent work on characterizing commodity serverless computing platforms. Serverless computing is an emerging paradigm for cloud computing, and it is gaining traction in a wide range of domains, such as video processing, scientific computing, machine learning, and big data processing. It has been estimated that the market of serverless computing is expected to grow from about $1.88 billion in 2016 to about $7.72 billion in 2021. In serverless computing, it allows developers to focus on only application logic without managing underlying infrastructure, such as load balancing, scalability, and other runtime issues. Moreover, for cloud providers, this paradigm allows them to better utilize cloud resources. Different workloads can be executed on serverless computing platforms, and users only pay for the actual execution time. These commodity serverless computing platforms operate in a black box fashion, so developers do not need to pay attention to the low-level implementation details. Therefore, it may be difficult for developers to choose the most suitable serverless computing platform to host their applications, or how to build their application in the right way on a serverless computing platform. These issues are important because they affect developer decisions, which in turn affect service quality, user experience, and even the app ecosystem. However, there is currently a lack of such a comprehensive knowledge to assist developers in selection and development. Thus, in this work, we conduct a comprehensive qualitative analysis and quantitative analysis of four mainstream commodity serverless computing platforms. They are Amazon's Lambda, Microsoft's Azure Functions, Google Cloud Functions, and Alibaba's Function Compute. Specifically, in qualitative analysis, we construct a taxonomy by summarizing characteristics from three aspects of development, deployment, and runtime. In the quantitative analysis, we mainly explore the performance characteristics of runtime. Next, we will introduce our results. For the first aspect, this is the taxonomy we built according to the official documentation. The specific instructions are skipped, and if you are interested, you can refer to our paper. We highlight our quantitative analysis results. We choose two types of benchmarks. One that only consumes specific resource requirements such as CPU or disk. The other is to use various resources such as multimedia processing, training, and interface tasks for machine learning. Based on these benchmarks, we investigate cold start latency, resource efficiency, and concurrency performance. In experiments with cold start latency, we compare the impact of different languages and memory sizes on four serverless computing platforms executing Hello World tasks. Based on these results, we conclude that, regardless of preference, developers can choose a lightweight language, for example, Python or Node.js, for developing shorter time functionality. For cloud vendors, they can further optimize the internalization of a tedious runtime like Java. We also compared the effects of package size on cold starts. We found that loading redundant libraries can introduce non-negligible cold start times. Therefore, developers need to prune their code, for example, removing useless code and imports, and apply lazy loading of libraries to alleviate internalization functions overhead. It is best for cloud vendors to provide relevant tools to help developers to optimize their function package before development. In resource efficiency experiments, we apply different types of benchmarks to compare performance. For compute-intensive and memory-intensive workloads, each platform computes differently. Developers can get more computing power by allocating more memory, but they needed to make a trade-off between performance and cost. For complex workloads, developers can allocate more memory to improve performance. These platforms can achieve relatively stable performance when memory size is set above 1 GB. According to our results, Alibaba Cloud Function Compute has a better ability to handle complex workloads. In our exploration of concurrency performance, we created 20 Python-based serverless functions with the same configuration and code, but different function names, and invoked each function in increments of every 10 requests. It can be seen from the experimental results that, first, AWS Lambda can execute more than 200 concurrent requests, which is stronger than the other platforms in handling a large number of burst concurrent requests. Second, we also find that concurrency performance of Alibaba Cloud Function Compute does not change with the number of concurrent requests, and it is also the best and most stable among these platforms. Additionally, AWS Lambda and Google Cloud Functions have similar concurrency performance, and their request execution time increases linearly with the number of concurrency. We also find that Azure Functions has the worst and least stable concurrency performance. For example, when there are 20 concurrent requests, the median value of the request execution time of Azure Functions in the figure is 445.83% worse than that of Alibaba Cloud Function Compute. Now, we explain the underlying reasons for their experimental results. The variation in their performance differences may be mainly affected by the scalability strategy of the platform, because commercial serverless computing platforms are black box. We can only analyze these strategies through collected data. On Alibaba Cloud Function Compute, it will launch a small part of virtual machines, and equably launch new function instances on these virtual machines alternatively for all concurrent requests. On Google Cloud Functions, it will generate a small number of virtual machines, and most new function instances will be launched on few virtual machines. On AWS Lambda, some requests will be executed on some function instances, and other requests will wait for available instances. If there are no available function instances, they will be refused to handle the remaining requests. On Azure Functions, concurrent requests can be processed by only a small number of function instances at the same time, and the rest will wait. The specific analysis process can be found in our paper. Finally, we give a brief summary of our work. We conduct a comprehensive study of 4 mainstream commodity serverless computing platforms. In the qualitative analysis, we characterize their development, deployment, and runtime phases. In quantitative analysis, we measure their actual runtime performance. Based on these results, we proposed a series of findings and implications to further facilitate the development of serverless computing. That's all my presentation. You can find more details in your paper if you are interested. Thank you for your attention.